All right, so did a real quick review with some of the people here in class about what we went over last class, notes jotted down there. Just to get our brains thinking about electron configurations again, go ahead and write out electron configurations for each of these elements. Notice that they're pretty big. They're relatively large elements. We do have a shortcut method that we learned last time. So I'll give you a couple minutes, jog your brain. Feel free to chat with your neighbor about what you're thinking, ask questions, etc. And we'll come back together in a little bit. All right, that was a little bit of time for the people in class. Probably not enough to get all of them unless you've really been practicing for some reason, which would be great. I just don't expect it yet. So hopefully you got at least to start on some of these, maybe got even the first one done. So for each of these elements, we're going to use our shortcut because I don't really like writing out super long electron configurations, even though I definitely can do it, trust me. So for aluminum, we're going to look at our periodic table up on the wall. Aluminum is in column or group 13, and it's in row 3. That row 3 part is important. We need to find our previous noble gas, which in this case is the end of row 2, neon. So we're going to use neon in brackets. That's our shortcut. And aluminum's number is 13. Its Z is 13, so it has 13 protons. That also means it has 13 electrons. Neon, being number 10, has 10 protons, 10 electrons, and so included in this shortcut, we've got 10 electrons baked in there. So 13 minus 10, we've got 3 electrons left to place. And going through whatever method you choose to figure out our energy level order, we're going to figure out our next energy level. I'm going to use the periodic table in class. So starting from neon, the next thing after neon is sodium. We're moving over into row 3. And so that means that the number that goes out in front to specify our orbital is 3. And first up, moving left to right on the periodic table, is our first 2 columns. That's our S block. So 3s comes up first. Our S subshell has 1 orbital. It's just that one spherical shape. Each orbital can contain 2 electrons. So we can place 2 electrons into our 3s2. Since we had 3 electrons to place, we still have 1 left. So we've got 1 electron left to place. What comes after 3s? Well, if we jump over from our S block, next up is our P block, and we're still in row 3. So we've got 3, this time P, and 1 electron can fit very well into that subshell. So that's our electron configuration for aluminum. Moving on to bromine, Br, we find bromine on the right side of the periodic table. It's number 35. Our previous noble gas is argon. Argon is at the end of row 3. And so we're going to use capital A lowercase r in brackets for our shortcut. Bromine, being number 35 on the periodic table, has 35 protons. It also has 35 electrons. Argon is number 18, meaning that it has 18 electrons, so we have 17 electrons left to place. We're going to follow the same strategy. I'm going to use the periodic table again. So if we look at what comes after argon, we're now in row 4. Row 4 means that the number that goes in front is 4, so we're in 4. First up, left to right, is our S block. So 4s, we can put 2 electrons into our 4s orbital. So we've got 15 electrons left. After our S block in row 4 comes our D block. What number are we going to put in front of the D block here? It is going to be 3. Who remembers why it's 3? Yeah, so 3 is the first time that the first principal quantum number level that D shows up in. So even though it's row 4, it's 3D, because D shows up for 3. So all of our D rows, it's going to be, in this case, it's 3D. It's in 4 for the period number or the row number. It's always going to be 1 less whatever the number is in our row. So in 5, we would be using 4D. In 6, it would be 5D, et cetera, et cetera. Okay, so we've got our 3D. How many orbitals do we have in our D subshell? We have 5. So our S is 1, our P is 3, our D is 5. We can also, so since we have 5 orbitals, each orbital can hold 2 electrons. 5 times 2, we get 10 electrons. You can also just count across. From scandium to zinc, we've got a total of 10 columns there, 10 groups. That works out for 10 electrons. So either way that you want to do it. So 3D10, we're going to put 10 into our 3D. So that means that we've got 5 electrons left. After our 3D, our top row of our D block, comes row number 4, and now we're in the P block. So we've got 4P up next. And since we have 5 electrons, and we've got 6 slots in our P subshell, we can fit all 5 of those electrons in there. So there's our electron configuration for bromine. Last one we've got here is strontium, Sr. We're going to look at our previous noble gas. This time it's krypton. Since strontium is in row 5, we're looking up to row 4. We find krypton, symbol Kr. Krypton is number 36. So it has 36 electrons. Strontium is number 38. 38 protons, 38 electrons, meaning that we've got 2 electrons left. Strontium is in row 5, and first up is our S block. So we've got 5s. S can hold both of those electrons. So that one's relatively quick and easy. Questions about any of those electron configurations? Great. All right, we can also do orbital diagrams for things. So let's do an orbital diagram for carbon. I feel like we did this last class, but oh well. So carbon is C, 6 protons, meaning it has 6 electrons. If we wanted to, if we really wanted to, we could do our shortcut for helium. Feels a little silly, but might as well. So after we use that shortcut, we've got 4 electrons left to place. You don't necessarily have to count out the number of electrons. You can also just read it off the periodic table, and we'll go over that again later in the class. So after helium, our previous noble gas, we're in row 2, and we've got the S block up. So 4s, we can put 2 electrons into 4s. We'll have 2 electrons left to go, and that brings us to our 2p. Since p, why did I write 4s? It should be 2s. So 2s2, and then 2p, we can put our last 2 electrons there. And then we've got our electron configuration, so we can now make our orbital diagram. So we're going to draw out a box for our 2s, And for 2p, which comes after that, how many boxes are we writing? 3 boxes for 3 orbitals, or 3 different dumbbell shapes. And our 2s was full, so we've got 2 electrons to place in there. We're going to place them up and then pair it down. And for our 2p, we have 2 electrons. How are we going to place them? Up and up in separate boxes. It probably doesn't matter if you put them both in the left 2-most boxes. You could probably put them in the right 2-most, or you could put them in the outside ones. Probably doesn't matter. I just fill them in left to right, so that's why it's that way. And they do have to be paired up because of Hund's rule, which we learned towards the end of last class. So there's our orbital diagram for carbon. So big part of the reason that we're learning about this, learning about electron configurations, is so that we can talk about valence electrons. I believe we've talked about them very briefly. We just kind of skipped past them. Valence electrons, valence just means outside. So these are electrons in the outermost principal shell in the highest n orbitals. And the valence electrons are important because those are the ones that are involved in chemical bonding. So this helps bring us into being able to talk about bonding between different elements, like in molecular compounds. So our outermost electrons can participate in bonding. And those are our valence electrons. The other electrons, so not our valence electrons, are core electrons. So if it's not a valence electron, it's a core electron. So all of the inner layers, however many we have, all of those electrons are the core electrons. Valence we can think of as just meaning outside here, or outermost. So if we look at an electron configuration for silicon, silicon has 4 valence electrons. We've got our electron configuration already written out, 1s2, 2s2, 2p6, and then we would skip down. Since silicon is in the 3rd row, we would have our 3s. We're past that, so 3s2. We're in the 2nd spot in our p block on row 3, so that's 3p2. And these outermost electrons, 3 is the outer shell here. And so the 2 electrons that we have in the 3s plus the 2 electrons that we have in the 3p make 4 valence electrons. And our core electrons is everything else, so 10 core electrons. Another way that we could have written this out, we could have used our shortcut, right, with neon and then 3s2, 3p2. If we use our shortcut, not always, but generally, at least for these smaller things, the number of electrons for our noble gas is going to be the same as the number of core electrons. So neon has 10 electrons. Neon's representing all of our inner shells. So conveniently here, it's also the number of core electrons. That's not always going to be the case. All right. Another exercise for you, write an electron configuration for chlorine, then identify the valence electrons and core electrons. You can use your shortcut. and I'll give you 2 minutes. All right, that was about 2 minutes in the class, so we're coming back. We want to write an electron configuration for chlorine. We find chlorine, Cl on the periodic table, it's got a number of 17, so 17 protons, also 17 electrons. Our previous noble gas is neon. Neon has 10 electrons, same as it has for the previous examples. So we've got 7 electrons left to place. Up next, after neon, we're in row 3. Row 3 means our number that we write is 3. And our first block that we encounter, moving left to right, is our S block, our first 2 columns. We're going to plop 2 electrons down. And so we've got 5 electrons left after filling up our 3s block. Up next, jumping across our transition metals, we get to 3p. 3p has enough room for 6 electrons, so we can very comfortably fit 5 electrons inside of our 3p. So symbol for neon, 3s2, 3p5 is our electron configuration. In this case, neon represents the core electrons. So chlorine has 10 core electrons. And our outermost electrons in our n equals 3 is 7. 7 electrons in n equals 3, so 7 valence electrons. Questions? Yes?
For transition metals with the electrons in 3D, are the valence electrons in 3D or 4s?
Valence electrons for transition metals, if we had something like manganese, which is in that first row, we'd be filling up our 3D. 4 is our highest number, so 4 is still going to be where our valence electrons live. And I think that actually comes up in a slide. Conveniently for us, the elements if they're in the same column, so our 1A through 8A, designations that you'll often see, that's conveniently also the number of valence electrons. So everything in our 1A column, we've got 1s1, 2s1, 3s1. Those all have 1 valence electron. If we move over a column, 2s2, 3s2, or also helium, we've got 2 valence electrons. If we jump across past our transition metals to our p blocks, we've got our 3s or our 2s filled, and we're also adding 1 in our p block, so we've got 3 valence electrons. So last number of the group number is the number of valence electrons. Except for helium. This also doesn't work for our transition metals. But for our main group stuff, which is mostly what we care about, things that aren't transition metals, this holds true. So this is really nice for very quickly being able to figure out how many valence electrons an element has, which you will want to be able to do, because we're going to be using valence electrons quite a bit later in the back half of this chapter. So for our valence electrons for a main group element, except for helium, it's equal to the group number if we're using that 1A through 8A. And the row number is the same as the principal quantum number, except for our D shell we subtract 1, for our F shell we subtract 2, which we've talked about a little bit. Here's a full look at our electron configurations on our periodic table and where we're filling things up. We're going to be using this for an example in a little bit. So again, we've got our S block over here on the left side. Just relabel it. A good reminder, our P block is all over here on the right side. Our D block is our transition metals, and our F block, which we're not going to touch with a 10-foot pole, is down below, our lanthanides and actinides. When we are in our transition series, or our transition metals, our D block, this represents the filling of core orbitals. Since 3D shows up in row 4, for example. So it's not our outermost layer. It's actually an inside layer that we're working on filling up. And we have a couple of exceptions. There's two weird ones, and I think I have a slide for this. There's two weird ones in our periodic table that might be helpful to know. I don't have a slide for that. Okay, so let's look at what that weird exception is, those two weird exceptions. We're going to be looking at our row 4. So we've got 2 boxes for our S block, our P block, I think that was in orange, go Tigers, 3, 4, 5, 6, 7, 8, 9, 10, and then our wall of P block. Okay, so our two weird exceptions are chromium and copper. Chromium and copper are weird because we would normally have, if we're looking at electron configurations, we'll do one for chromium and one for copper. What we would expect to see is that our S block is full, right? We're past our S block. We're already in the D block, so our S block should be full. And then when we get to our D block, we've got 5 orbitals. And when we're at chromium, we're in our 4th spot, so we would have 4 of these orbitals filled. We'll do those in green too. So that's the expected orbital diagram for chromium, just based on what we know for class. However, you might notice we're very close to having a nice, full, in-sync, half-filled d orbitals. Right, we've got 4 up arrows. If we just had one more, we'd have 5 up arrows, right? They'd all be nice and in sync and in parallel, and that would be really nice and great. And chromium also thinks that. And so what we actually see is chromium says, yoink. We're pulling that electron, and we're filling up, we're half filling our d orbitals. Because of that symmetry, there is actually like the parallel spin, the symmetry. It's nice and stable, and so it will actually pull one out of there. And so this is our actual with the adjustment made in red. And so our row is 4, so we're 4s1 instead of 4s2, and we are 3d5, which is not what we would expect. when we are over in copper's position, copper is in the 9th spot. So we've half filled it, and then we've come back and almost completely filled our D subshell. And the same thing happens. We're really, really close to having this D subshell, these D orbitals completely filled. And so it just goes ahead and pulls one of those electrons out from the 4s to fill in that shell. So again, we've got 4s1, but this time we've got 3d10. So those are two weird exceptions that show up in our transition metal series for valence electrons. At most, I would expect to have maybe one question on exam 3 about this. At most. So if you'd like to just ignore it, save brain space for something else, that's fine. Questions about that? The important takeaway from this slide is that when we're in our transition metal block, we're filling up our core orbitals. We're not filling up our valence electrons. All right, using the periodic table to find an electron configuration we're going to show for phosphorus. So we would start off finding our previous noble gas. So we can write out Ne in brackets to start off our electron configuration. Then we look to the next row. And we'll start counting across each element at a time. So we start off, we're in our first spot of our 3s, we're in our second spot of our 3s. That means we've got 2 electrons in 3s. We're past 3s. So 3s is full. And that means 3s2. We skip over our D block, and now we're in the P block. The position in the P block, that's a bad color. Let's try blue. The position that we are in each row represents how many electrons we have added to that particular row and block combination. So we're in the 3s area. We're in the 4th spot, meaning we've got 4 electrons placed into our 3p, so 3p4. This is how I do electron configurations when I have to do them. Once you learn how to do it, you'll be wicked fast at them. Because you just look, what are we past? We're past 3s, so 3s2. We're in 3p. We're in the 4th spot, so 3p4. It's super, super fast and easy once you learn how to do it. You don't have to use this method. It's what I use. I like it. If it works for you, that's awesome. Questions?
I'm kind of confused about, is that sulfur?
That is sulfur, yeah. So for
So you don't skip over, okay.
so we'll change the slide. It is supposed to be sulfur, yeah. It's a fun mismatch. Other questions? All right, and then this is just like the text block that explains that. So I'm going to skip over that. All right, here's a generic periodic table. Use the periodic table to figure out the electron configuration for arsenic. All right, so we are going to start off with our previous noble gas. What is our previous noble gas? So argon is our previous noble gas. We're going to use that as our shortcut. And then we look next at our row 4, because that's what comes after argon. We are past our S block. So S block is full. So 4S is full. We are also past our D block. So our D block is full, or our not 4D, 3D. So 3D is full. That means we've got 3D10. And we are in the third column, or the third spot in the P block. So that means we are in row 4P3. So that's how we might do it for arsenic and other elements. So one of the reasons that valence electrons are so important is that they determine a lot of the properties of the element. So part of the reason that our periodic table is structured the way that it is so that we can glean extra information out of it. You may remember that from was it chapter 1 or 2, talking about Dmitry Mendeleev, who's the person that came up with the idea of putting them in this order rather than just lining them all up in a nice rectangle, basically. So we can draw out extra information from our periodic table based on the way that everything is set up. So each column or group has similar properties, or each element in a column, rather. And we're going to talk about what some of those properties are. We've mentioned them a little bit, but we'll talk about them now, including some explanation with our electron configuration and valence electrons. And this is because of the number of valence electrons. Starting off with our noble gases, our atoms with 8 valence electrons, or 2 for helium, are predicted to be very low in energy. This is because they have full orbitals. So like helium has just a full 1s, neon, and all the other things below it, their valence electron shells are going to look like this. Completely filled up, all of our electrons are paired. We get that nice kind of synchronization between our electrons. We don't have any extra electrons sticking out outside of our shell, and we don't have any wedges or gaps in the shell that we're currently in. So if you think of like an onion, if you've got a little part of an outside shell, it's pretty easy to rip that off. Or if you've got a deep gash into your onion, it's a little easier to pull those layers off. Those are some things that come to mind for me. Because they have these full orbitals and they're very stable, they are relatively inert or non-reactive, famously inert and non-reactive. Noble gases, as a general rule, don't participate in reactions. They've got all the electrons they need, and they're not trying to lose any electrons either. and so they're not going to participate in reactions. This is also why you can, if you have a helium balloon, some of you may know that, hopefully all of you know, you can kind of breathe in some of that helium gas and then talk, right? And your voice gets pitch shifted up. Are we aware of that phenomenon, that fun party trick? And it doesn't kill you, right? Like it doesn't hurt you at all because the helium goes in and it comes out. It doesn't react with anything. It's not a big deal. And helium being less dense than air, it normally floats in air. Since it's less dense, it flows out faster, and that's why your voice pitch shifts up. There's another fun thing that you can do. If you ever get your hands on argon gas and you're around somebody that's not going to be mad at you, argon gas will also pitch shift your voice. And you can find videos of people doing this. But argon gas is more dense than air, like significantly more dense than air, and so it'll actually pitch shift your voice down. And again, since it's a noble gas, you'll breathe it in, you'll breathe it out. It's not a big deal. It's not going to hurt you as long as there aren't any contaminants in the gas. I haven't tried that one, even though I have had access to argon cylinders. I just am too scared of getting in trouble. So, you know, my two shoes and whatnot. But if you get a chance, that might be something fun to try, or just watch a video, because that's even safer. And everything, essentially, all of the other elements, we can think of them just wanting to be like these noble gases. They want to be these gas nobilities. And so if things are really close to noble gases, they will very rapidly lose or gain electrons to try to become like a noble gas. So talking about alkali metals next, our alkali metals being our first first column on the periodic table. If they lose, not if they lose 1 electron, they have noble gas configuration, electron configuration. And like we were talking about with our noble gases, they're very stable. And so it's favorable for our alkali metals to lose that 1 electron, basically get rid of that outermost shell. Let's look at that for sodium. So for sodium, our electron configuration looks like this. We've got our n equals 2 here in red, and our n equals 3 here in also red. I'll change that to blue. So if we get rid of that 1 electron, then we completely get rid of this n equals 3 shell, right? Pretend like it's not there. And now we've got a full n equals 2 shell. Very stable, very good. We love to see it. Noble gases hate this one trick, right? Lose 1 electron, suddenly noble gas. So that's why all of our alkali metals, our group 1 metals, tend to lose 1 electron. It's to get them back up a row to have an electron configuration like a noble gas. We get that noble gas configuration that we want. And so that's why our alkali metals are especially reactive. You can find fun videos of people taking pure alkali metals and putting them in water. And like lithium reacts pretty strongly, sodium reacts even more strongly. I think sodium and potassium both, like if you just put the metal in like a beaker of water, it like lights on fire and dances around the surface of the water. And once you get to cesium, cesium's the most reactive of the group, it like basically makes an explosion. like a giant explosion when it reacts with water. Our alkaline earth metals are right next door, but this time, if this is our n equals 2 and we're looking at magnesium, we've got in our n equals 3, 2 electrons. Since we've got 2 electrons are harder to lose. And by lose, I mean give away. So our alkaline earth metals are less reactive. Compared to our alkali metals. They're still relatively reactive, and if we can give away these 2 electrons, losing 2 electrons, losing 2 electrons means 2 plus ion. And so that's why all of our alkaline earth metals form 2 positive ions. It gets them back to that noble gas configuration. Flipping over to the other side of the periodic table, looking at our halogens. Our halogens are in the opposite camp. So let's look at fluorine. Our electron configuration for fluorine, we've got our 1s, our 2s, our 2p, and it's going to look something like this. So we are 1 electron away from becoming neon. So if we gain 1 electron, then it has noble gas configuration. Which is a full outer shell. If you gain 1 electron, electrons have a 1 minus charge, so all of our halogens, that's why they form 1 minus charges when they are ions. This also makes our halogens really, really reactive because it's relatively easy to pick up 1 electron. And fluorine is the most reactive. I actually have a video in my YouTube watch later that I've got saved that's about fluorine and why chemists are apparently scared of it. It's really, really reactive stuff if it's not in the F2. I think if it's just F by itself, really nasty stuff. There's also a fun video of the Royal Society of Chemists, the chemical society in the United Kingdom, where they react fluorine with cesium. Fluorine, the most reactive nonmetal, reacting with the most reactive metal. And it's quite a challenge actually just setting that up, so that's a really cool video. Definitely recommend. And then the same ideas apply to our 6A and our 5A. For our 6A, we have to gain 2 electrons, so that's why we form a 2 negative charge. For our 5A, gain 3 electrons to become like a noble gas. Aluminum's the same idea as for our 1A and our 2A, and then zinc and silver are just weird. So that's the explanation for why these elements form those ions, which is hopefully helpful for remembering. Any questions about those before we get into some periodic trends? Fashion on the periodic table. All right, so our trends on the periodic table. So how do these things change as we move across the periodic table, left to right, right to left, top to bottom, bottom to top, is what we're looking at. So we're looking at how these change generally across and down the periodic table. This is just a very qualitative approach. We're not really using a whole lot of numbers for these periodic trends. Just if we had to compare two things that are sitting next to each other or two things that are located relative to each other, what do we expect the outcome to be? And if you're taking Chem 1A, these periodic trends will come in handy, if you know them, in Chem 1A. So the first one that we're going to talk about is the atomic size. So since our atoms have those valence shells, they've got layers of electrons, right? If you add a layer, it's going to get bigger. And that's our first bullet point here. Size depends on the principal quantum number. Sorry, our second one. Wait. It's on the next slide. We're going to start with the not intuitive one first. We're moving across a period. So we're moving left to right on our periodic table. Our size is not going to increase, even though you would expect it to increase. So left to right, size decreases. Our size is based on principal quantum number n, so like the number of layers that we have. When we're moving left to right across the periodic table, we are in the same n number. So we're not changing the number of shells that we have, same outside shell size. What we do have is the number of protons in our nucleus, our little bit in the middle. So I'm going to we'll draw it out as an orbit. So we've got protons inside of our nucleus, and we've got our electrons out on these orbit paths, right? As we're moving left to right across the periodic table, we're increasing the positive charge on the inside. Increasing the positive charge means that we've got more of a pull on our electrons, and we're actually going to shrink that outer shell, but just by a little bit. So increasing the charge in the nucleus. Pulls the outer electrons in. And that causes our size to actually decrease. Again, this is as we're moving left to right across the periodic table. For a lot of these trends, if you don't want to understand the underlying reason or it's just not making sense, you can just put them on a flashcard. There's basically two different options for trends. So that's for our left to right. And for the top to bottom, when we're moving down the periodic table, down a column, size increases. We are adding layers to our atom. So let's think about hydrogen. Hydrogen's going to have just the one s. We'll go ahead and draw in one electron. If we move down to the one that's just below it, lithium. Lithium, if we're thinking in the Bohr model, we're adding another shell. So naturally, adding another shell, adding another layer, it's going to get bigger. So that one we do expect. That one makes sense for most people. If you want to think of it in terms of Which direction does it increase? It increases size moving right to left and top to bottom. So let's choose the larger atom in each of these pairs. And I thought that I had periodic table here, but I don't. So we're looking at PB and PO. Those are going to be in the bottom right side of the periodic table in our S block. The relationship to each other is we've got PB, and then skip a space, PO. Which one of those two atoms is going to be larger? PB or PO? It is going to be PB. PB is larger. They're in the same row, so they have the same number of shells. We've got fewer protons in the nucleus. So the valence electrons are a little bit further away or aren't pulled in as much. Or you just memorize our size decreases left to right or increases right to left. So that means the left side of it is going to be bigger. So PB. And then we can do RB or NA and their relationship to each other. Former lovers, now estranged. Oh wait, one's higher up in the same group. So which of these two atoms is going to be larger? It is RB. Larger because of more shells, we'll call it, or layers of electrons. Principal quantum number is larger, so RB is larger. Okay, thirdliest, we've got tin or bismuth. SNBI. Now we've got to think in both directions. So thinking about the left to right, which is going to be bigger? If they were in the same row and we're just thinking left to right, which one's bigger? Yeah, tin would be bigger. If we're thinking up and down, which one is going to be bigger? Okay, so we've got some competing forces, and we would kind of have to make an educated guess here. I would guess, and I think I'm correct about this, bismuth is going to be the larger one. That little difference in pulling the electrons in or letting them expand a little bit, not as big as adding a whole new layer. So bismuth is probably, and I think I'm correct about it, bigger. If you're sweating, worrying, how would we know that on an exam, Mr. K? The answer is, I won't give you a question like that. So you don't have to know that on an exam. You'll either get, it's just one simple atomic trend, so it'll be left, right, up, down, or the forces should add up. So that's the secret. All right, and then we've got fluorine or selenium. And they are arranged this way. Which one of those is going to be larger? Yeah, it's selenium. Left to right, selenium is bigger. It doesn't have that electron shrink. And if we're looking top to bottom, selenium is bigger. It's got 2 extra shells on it. It's definitely bigger. So the clear-cut larger atom is selenium. Questions about atomic size? Very cool, very cool. Another periodic trend that we have is ionization energy. Ionization energy is the energy required to remove an electron from the atom in the gaseous state. And possibly the keyest part of this, remove an electron. The gas state part, not really quite as important in my mind. For ionization energy, we're talking about losing an electron. How much energy does it take to pull an electron off? Our ionization energy increases as we move to the right across a period, a row. If we think about our extreme ends, all the way on the left side of the periodic table, our group 1A, it practically wants to lose an electron. That moves it to noble gas configuration for its electron configuration. If we're all the way on the right side of the periodic table, like fluorine or chlorine, to get to a noble gas configuration, the fastest way there is to gain an electron. So if you're moving the opposite way, that's the last thing that they're going to want to do. So it needs to gain 1 electron to get noble gas configuration. Losing 1 electron is the wrong way. So we've got very, very high ionization energy. Takes a lot of energy to remove. So that's our left to right. Our left to right increases, and as we move down a column, as we're moving down a column, we're adding new layers, remember? And the further those electrons are, the easier it is to remove. So it increases when we're moving up because we're getting smaller atoms. Electrons on big atoms are farther away. And if we think about them as magnets, because they're basically magnets, we've got 1 magnet in the middle, that's our nucleus. Our electrons in our outermost shell, those are the ones that we'd be losing. That's another little magnet. The further those magnets are away from each other, the easier it is to pull them apart. If you get really 2 strong magnets and you stick them right together, you're going to have a hard time pulling them directly off of each other. If they're like stuck to your hand, like on opposite sides of your hand, those would be pretty easy to remove. They might not even stick. They might just fall off. So that's what we're doing with these electrons. That's at least what my brain's thinking about. Okay, so ionization and atomic size are inversely related. So the trends are opposite. For our ionization energy, it increases in these directions. And for our atomic size, it increases in the opposite directions. So those are two of our trends. And there's our ionization energy trends on a chart. I think we have one more trend. We'll go ahead and power through. All right, for choosing the element with higher ionization energy, we've got first up magnesium and strontium. They are in the same column. Mg and Cert. We want the one with the higher ionization energy. Ionization energy increases as we go up because we're getting smaller. Harder to remove an electron from a small atom. And then we've got indium or tellurium, IN or TE, and their relationship. Something like this. Which of those is going to have the higher ionization energy? It is TE, because we're removing an electron. TE is closer to xenon in terms of gaining an electron, so it really doesn't want to move the opposite direction. Indium, it only has to lose 3 valence electrons, and then it's got that krypton configuration. So tellurium has the higher ionization energy. And then we've got carbon or phosphorus, and they're located like this. So we've got an increase in energy. If we're looking at, let's look left, right first, actually, because that's what we did last time. So left, right, phosphorus is higher. And if we're looking top, bottom, carbon is higher in terms of energy. For those of you on the recording, I'm throwing my hands up in the, I don't know, doing the little emoji or whatever. So I wouldn't expect you to be able to make a guess about that even. And then for fluorine and sulfur, F and S, we've got left, right, fluorine is greater. And if we're looking at the top down trend, fluorine is greater. So we're getting fluorine. Our last trend that we're learning is metallic character. Metals like to lose. Specifically, they like to lose electrons. So we're basically thinking about how easy is it to lose an electron? There's another key way of figuring out the metallic character. This is kind of like the opposite of ionization energy. Ionization energy, how hard is it to remove an electron? This is how easy is it to remove an electron? So it's going to decrease to the right, which means it increases to the left. I think that this is one of the easier trends to remember. Where are most of our metals on the periodic table? On the left side, and our nonmetals are on the right side. So it would make sense that if you're on the left side of the periodic table or further to the left, you're more like a metal. You're closer to that metal area. If you're further on the right, you're less like a metal, so lower metallic character. The metals are on the left side. So it follows that further left equals more metallic. And it also decreases top to bottom. Again, because they're getting bigger, so we've got more shells. The shells are further away from the nucleus in the middle. Easier to pluck off or remove those electrons. And I am not going to go over these because we've run out of time. If you're like, wow, these periodic table trends are really fun, it would be really fun if there was a game based on them. There is. It's called like Periodic or something like that. I played it one time and I won, and it's not my game. I don't own it. Don't accuse me of that. But it is something I would do.